Chapter 25. There's going to be a lot of topics that aren't very deep in this chapter. Chapter 26, we're going to apply them all sort of in great detail, and things get a little complicated there. So let's start by talking a little bit of magic. By magic, I mean chemistry. By chemistry, I mean, chemistry, okay? We don't really need to know the details of everything that's happening here. I just want to point out the basics of a battery, since we're going to be talking so very often, not just in the last chapter, but going forward, about this magical device that produces a potential difference for us. So the basic idea of a battery, and one of the most simple batteries we can construct is there on the left. If you just take a dilute acid and two different materials in that acid acting as electrodes, you kind of get this little process where, I don't know, you could maybe think of this one being very, very slowly dissolved by the acid, and it sends, as you see below here, positive ions into the solution as that dissolving happens. So maybe imagine leaving this as like little positive guys. How's that? Yay, fun. So if I do that, that's going to leave net negative charge on that particular electrode. So let's just go ahead and fill that in with negatives. But simultaneously, well, the acid, which is also known as the electrolyte, is becoming net positive because positive ions are heading there, which means that now it's going to attract electrons from the other electrode. So now we might imagine that negatives are going this way, negative, 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 leaving net positive on that electrode. Clearly, this is something that, well, if it's slowly dissolving, can last a while, but it's also something that's physically dying from the moment we set it up. It's almost like us as humans, right? It's like, you are born, and now you're dying. How depressing is that? It's all downhill from birth in a way. So sad. So that's what's happening to the battery. Maybe it lasts a short period of time. Maybe it lasts a long period of time, but it's not going to last forever. So you can imagine that the basic concept can be modified a number of different ways. We've got two different metals that we're using as electrodes and an acid that we're using as the electrolyte. There's a lot of experimentation that's been done and a lot of experimentation that can be done to vary those concepts and try to get larger and larger potential differences. It's really all based on the materials of the electrodes and at what rate they dissolve and how much they dissolve, leaving the net positive and negative charge behind. That gives rise to different amounts of potential difference between those two electrodes or those two terminals. Now, a battery like that's not terribly useful, right? Can you imagine if it was like, well, time to charge my phone again. So this battery died. I need to get my new beaker of acid, right? Yeah, and put two big rods in it. And then I take that and I like have, I don't know, maybe we bring fanny packs back or something. And like we like, and you like set it right there. You're like, great, that should last me a day. And then you walk around with your phone all day. That'd be fantastic. No, not terribly useful, especially somebody bumps you. Like, well, you know, somebody bumps you and you're like, oh, that's half my charge for the day because now my leg's on fire from this acid, right? So just bad all the way around. So clearly we've advanced quite a bit beyond this and even way beyond, of course, what we see up there, which is a more common and convenient configuration where instead of dealing with just a liquid acid and having two distinct electrodes, things are in a cylindrical configuration where now we're using an electrolyte paste. That sounds better. We should use that in the beaker to carry around with our phone. That's less likely to spill. And now the two terminals, one is going right down the middle and one is the outer casing. Same thing, but clearly more compact. That's just a standard battery that you might put in a flashlight or something, but, you know, open up your phone. Please don't first, you know. You're going to find this idea, but in more advanced configurations. The concept's the same in all cases. If you want to make a difference in technology, go do battery research. Help us. We need breakthroughs. And when I say we, I mean like the universal we, not we, me. Like, I don't need your help personally because I have nothing to do with any of this. But in general, increases in battery technology, both in how fast they can charge and how long they last, and shrinking the amount of size, can make differences like across many, many different industries. And it seems like over the last few decades, it's been like all of these incremental improvements. Like, things have gotten better, but like there's a breakthrough that needs to happen. Something where there's like an order of magnitude reduction in size or increase in capacity or something before we can really move forward. Yeah. What is my area of research? It is non-existent. That's a good question. Yeah, I research non-existence or death. No, I don't research anything. I'm a lecturer officially. Yeah, which means I only get to do this, which is fantastic because I got out of the research game about a decade ago because I was tired of it. Yeah, just didn't do it for me personally. And then I found something I like. So, alas, here I am. Yeah. Whoa. What did I research? I researched non-existence. Now, I'm going to make that joke again. I researched thermoelectric materials, which in a way is kind of like this semester in a nutshell, right? Electric. Thermoelectric materials, it turns out, are materials that when you make a temperature gradient across them, make one side hot, the other side cold, they generate a voltage, which is kind of cool. And vice versa. If you force them to have a potential difference, one end gets hot and the other end gets cold, which is kind of nice. People were interested in trying to use it in refrigeration and air conditioning technologies because it's solid state and it would be better than having to deal with like various gases and things that are being transferred. But alas, the efficiencies are very, 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 very low. And I don't think anyone has cracked that nut yet. I was doing basic stuff. As in the magic people, the chemists, were like, we made a thing. And we were like, ooh, that thing someone thinks might be good as a thermoelectric material. And then I did things like measure their resistance and thermal conductance and other various properties to determine if it would be appropriate. And then I got tired of that. Very tired of that. Someone go take my place, please. Any other questions? Are these the personal questions today? Yeah. The zinc casing? Which zinc casing where? Oh, over there. Magic chemistry. How's that? I did not like chemistry. You know? Any other people with me here? It was the worst. Yes, thank you. Anybody out there who thinks physics is the worst? Yeah, I figured there's probably a few. You're thinking like, you've got no right to talk. This is the most terrible thing I've ever seen. So this next slide, I got to say, that is some beautiful artwork. One of these semesters, I'm going to get to this point in the semester, and I'm going to have my special outfit that I wear that day, consisting of a white T-shirt and strange-looking blue jeans that are a little too short and white sneakers. And then people will be like, ooh, he's wearing something different today. And then I'll get to this slide and see if anybody notices. I don't think anybody's going to notice. Or maybe you will because you'll be like, odd, what's up with him? So, first of all, I'm quite curious if these are the same people because they all kind of look the same until you zoom in. Get that face in your head. Are you ready? You got it? Not the same person. They actually took the time, right, to draw different faces. Who cares? Are they the same over here? I think that's the same first guy and the same second guy. So they drew two different faces. If it were me, I would have just gone like this. Person. That's the way you do artwork without wasting too much time, all right? Person, and you can be like, ooh, grass. See, that's lovely. What we're trying to point out here is how does this potential difference give rise to anything? And I think this is a relatively simple concept and maybe one that you're already somewhat familiar with, but I want to make sure that we're all thinking about charge flow in the exact same way. So why do charges go anywhere? The way I like to think about this is twofold. First of all, what makes charges flow around a circuit is that they are given a place to go, first of all. We give them a path. We talked about that when I introduced circuits right at the start of dealing with capacitors in series and parallel. We said, well, they've got to have a path. They have to have a closed conducting path made up of conductors so that the charge can go somewhere. But also we have to give them a reason. So we'll say are given a reason to go. The reason to go is the potential difference. The path is a closed circuit. So we see this reason to go illustrated in this particular diagram by two random dudes in blue jeans holding a hose that apparently contains water, even though the hose is green. That bothers me for some reason because I want to be able to see the water. So let's pretend that there's water in there. There we go. If the two ends of the hose are held at the same level, clearly all the water is just going to stay exactly where it is. It has no reason to go anywhere. What we might say is that the water at one end and the water at the other end possesses the exact same gravitational potential energy. Or if we wanted to talk in terms of more electrical things, maybe we would say that the position of one end of the hose is at one gravitational potential and the other end is at the same potential. There is no potential difference between one end of the hose and the other. The only way that I can get water to flow is by creating a potential difference. And you can see that this one dude on the right has decided to get his shoes wet, apparently. So he lowers the end of the hose, meaning that the potential of that end of the hose is lower, and now, well, water can flow. If I do this exact same thing in a circuit, charges will flow. The analogy holds. If I have one part of the circuit that's at high potential, another part of the circuit at low potential, the free charges that are in those conductors will go from high to low potential. Okay? So, a few different things here. The potential difference, well, obviously, is created by the battery that we had on the previous slide. And the second point that we should make is that there is a bit of a misnomer that is commonly used that kind of causes problems. Something known as the electromotive force. The electromotive force is really this thing above, the potential difference that's being created by the battery. The thing was, historically, like, people are detecting charges moving from one point to another, and thinking from sort of a Newtonian perspective, you think, something's moving, there must be a force. Well, that's one way to think about it, right? The thing is, the thing that we now call voltage, they mistakenly named a force, which causes problems with everything that we've learned. So the units don't match up, the names don't match up. I just want you to know that if you hear EMF or electromotive force, it's not a force. It's a potential difference. Okay, and that's what's being created by the battery. Yeah.
Is it EMF also
I mean, it could be. I don't think I've seen electromagnetic field abbreviated that way, but there's no reason not. The acronym still works. But, yeah. If it's not clear, just ask. Okay? So, electromotive force, not a force. We should just write that up here. Not a force. What we maybe should say is that it is a what? No, think funnier. Think hilarious. Think me hilarious, right? As in not really funny. See, we could say not a force, but it is a farce. Yeah, that's terrible. I'm going to erase that because that should never exist. In fact, let's just get rid of all of this. I'm done. I don't know. Whoops. Let's make it go back. There we go. Back again. Let's just get rid of this part. Oh, there we go. All right. Let's see if there's anything else that I wanted to add to this slide. Actually, I haven't even opened the notes for this chapter yet. We should do that and see if I've missed anything. We talked about that. We talked about that. That's good. That's happy. Okay. So, charges flowing. We haven't described what that is yet. Anytime I have a flow of charge from one place to another, that is given the name current. Much like if I have water that's flowing from one place to another, like in a river, we would call that a current. So the description of these things is basically the same. If we wanted to describe this mathematically, we could do a couple of different things. We could describe an average current. And we use I for current. Who in the world knows why? Anybody? Do you have the answer? I don't. So if you can help, that'd be fantastic. Add to the class's learning. Why do we use I for current? Latin or something? Probably. Yeah. History and other languages. Why not? So the current I, the average current, we should put a bar over that, is an amount of charge that passes by in a given amount of time. So it's a rate of charge flow through a particular region or area. If we wanted to instead make this an instantaneous current, I always get lost in the word instantaneous. Anybody else? You get about halfway through there and you're just like A's and E's and things are just happening and you're like, I need a T. Where should the T be? And then the next thing you know, the word's over and you're happy. So instantaneous current. We'll just write that as I would be the derivative instead. So instantaneous or average current. If I just look at both of those equations so you can see what the units might be, we've got coulombs in the numerator. Look, I'm getting lost in another word now. And we've got seconds in the denominator, and that thing is known as the ampere or amp. Unit of current is the ampere. So, if we were to connect all this together and create another basic circuit, we already did this a little bit with capacitors, but perhaps even more basically, we've got a potential difference being created by a battery. We've got a bunch of conducting surfaces or wires. Over here we have a very lovely light bulb, don't you think? Look at that. Look at how it glows. That is beautiful. Yes, I want those in my house. And then at the top we have a switch. You can see that the switch is currently open. There is not a continuous conducting path until I close the switch. You might see that this schematic on the left, which is just a representation of a basic electric circuit, could be represented again by dudes in water, okay? So in this particular case, we just have one dude who's wearing a different color shirt. And now, once again, let's zoom in and see if he's one of our friends from before. No? You don't recognize him. You know for sure he's a different guy? Wow, you people are good. I have to go back and check. I don't know. Yeah, it's not him. And not him. Okay. Now we know. Nobody really cared, though, did you? Also, notice our new person has a sort of disjointed arm below the elbow that can magically float through the air. So everything is weird about this particular guy. So you might imagine that this guy who's lifting up the water from one level to another, you could think of him as the battery. He's doing work on pieces of water to change their potential energy. He's doing that by raising them from a location that has a low potential to a location that has a high potential. He's moving them through a potential difference. He's doing work on the charges to change their potential energy, okay? Once the charges or the water is up there, well, it's like, ooh, if I give them a path, they can flow. And then maybe over here we could get them to turn something and do mechanical energy. This would represent our light bulb. And then, of course, all of this water just pulls here and goes back to the start. We have a complete circuit. We have a potential difference. And we've even got something in there that we can extract a little bit of work out as the water falls from one potential to another. So notice a couple of different points. We already said we need a continuous conducting path in order for the current to flow. So if I go back up to my diagram, if this switch is open, it's not a continuous conducting path. If I go over here to the side and decide, I don't know, just to make a barrier here at the bottom, well, the water can't continue in a loop if it has no way to get back to the beginning. In that particular case, I don't have a closed conducting path. So just as a matter of terminology, we could say that if I have a continuous conducting path, this is called a closed circuit. And if it is broken in some way, we call that an open circuit. And I feel like those two words just have a backwards connotation about them. Something about open, you think of like, yay, it's working. Things are happening. Well, that's not what's happening here. If it's open, it's bad. Okay? So just kind of get that straight in your head. One other thing I should point out is that charge is conserved. I don't want you to get in your idea that I don't know that the battery is like a tank of charge, right? And then somebody takes the battery and pours it into the circuit, and then it goes into the circuit, and eventually the battery's empty, and it has no more charge, and life is sad. Things aren't working that way. Instead, the battery is just providing a difference in potential. It's doing work on charges to maintain a potential difference, but there's charge everywhere in the circuit at all times. All of the conducting wires have charge, much like we drew over here on the right. All of these parts in the circuit have water, okay? So that when I give them a path, when I make this connection with the switch and I have this potential difference, you can imagine that charge everywhere in the circuit immediately begins to move. It's not like the light bulb has to wait for some charge from the battery to travel this distance and get over there. Instead, I make the connection, there is a potential difference as like everything everywhere begins to rotate around the circuit. Okay? Can you imagine how impractical, perhaps, using electricity to power things would be if I had to physically wait for electrons to get from point A to point B? You're like, well, kind of depends on how fast they travel. We're going to see later in this chapter that they travel really, really, really slowly, like depressingly slowly. So much so that if we had to wait for a reservoir of charge to get charge to the lights in this room, it might be maybe that's what happened. The lights aren't working. Maybe all is lost, and this has reverted to a reservoir of charge. We'd have to come into the room and be like, okay, it's midnight. There's class tomorrow. Let's turn on the lights. And then all of a sudden the charges might begin to flow to the things, and maybe by noon the next day, maybe not even then, well, they would have electrons and things would light up. Doesn't happen. As soon as I make the connection, charge flows everywhere. Notice, charge isn't used up. It doesn't get consumed. It doesn't get burned. It's just flowing around, and it's not produced by the battery. The battery is only giving us a potential difference. Thoughts and questions before we do one more slide. You look like you're losing it. In the back, you said before everything was still good. Is it still good, or are you now, no, it's not? I can tell. Just look at him. Man, that is sad. I'm sorry. Do we need to do exercises or something? We should have an exercise break halfway through class where we all run around the room 8 times. That sounds terrible. I don't want to do that either. Your question.
Yeah. Why is it? I'm not getting it. Why is it charging up in the circuit? Because in the battery, in the very starting time, when you made a connection, doesn't the electrons flow from one metal to the other?
They do, but they're not disappearing. They're just going to a new place. So, if anything, we're redistributing charge, but we're never consuming any. It can end up in a place where I can't easily get it back and get it to do work for me, but that doesn't mean the electrons have been destroyed. They're just in a new location in the circuit. Okay? One more slide. You can do this. Stay with me for a moment. So what about this electron moving around? There's a few different issues. First of all, this first one we already talked about. Charge flow begins everywhere in the circuit immediately. If it helps, one way to think about this is when I make a connection, an electric field is generated everywhere in the circuit that sort of tells the charge to move. An electric field can be generated and propagate at nearly the speed of light, so it's like flip the switch. Well, instructions are given up at the location of the light bulbs in the circuit to tell charges there to begin moving almost instantaneously. That's good. That's because of the creation of an electric field. We are going to have to do this thing because that's typically the way it's done, which is be consistent with everything we've talked about so far. When we defined the electric field, we said it's based on the direction that a positive charge would be pushed. That's the way the electric field vector points. We're continuing that idea even when we work with circuits, which means we have to pretend that it's positive charges that are moving. Just like we did with the capacitors. We said, yay, positive charges are leaving the battery and filling up the plate. I just don't want you to forget that the positive charges are bound in the nuclei of the atoms. They're not going anywhere, okay? They're not actually moving. We use this to match the convention of the electric field. So the math and everything still works out, but I just want you to remember that it's actually electrons that are going from point A to point B. So when we talk about charge moving everywhere in the circuit, the positive charges, the protons, are relatively fixed. It's the sea of electrons, roughly speaking, that's flowing throughout the circuit all at once, all right? So that means we end up with a diagram like on the top right. We define the direction of current as being from the positive to the negative side of the battery. And that's all based on the idea that positive charges move in the direction of the electric field. But what's actually happening, as you see there in red, is that electrons are flowing through the circuit in the opposite direction, okay? So there's a point of, I guess, convention, the way everyone's decided to describe these things, which we might call conventional current flow. The thing is, the other thing is in reality what's occurring, and it just doesn't matter for any mathematical reason, all right? The exact same results work out. Notice that one last diagram there. When we talk about electrons moving, this little red thing here, this is one electron. There we go, minus E. One sad electron. I don't want you to also think that it's like the water flow, where we imagine like, ooh, there's water everywhere in a hose, and it's like all the water just goes and just flows in one direction. The electrons aren't doing that. It's not like there's just like a bunch of electrons and they all decide all at once, let's all go that way. Yay, fantastic. Instead, they have to contend with the fact that there's a bunch of other electrons and there's all those nuclei of all those atoms that are in the way. And as we've learned back in thermodynamics, that with temperature, those nuclei are moving around and vibrating and everything. So you can imagine this one poor electron, like he gets the command from the electric field to say, go that way. And in front of him, he sees like this gauntlet that he has to run, right? All of this stuff is like moving around like this. And he's like, I got to go that way? I don't want to go that way. That looks terrible. So this is what happens, right? His path looks more something like this. He's like, okay, here we go. And then he's like bouncing up against things and then bouncing over here. And he continues to have all these collisions with things as he tries to go in the direction that the electric field is telling him to, which means that it's not going to be a direct path. It's going to be more of a meandering path. We say that the electron drifts from one place to another. And that has a name that we'll see later in this chapter, and we'll derive where this comes from, known as the drift velocity. On the last slide of the chapter, we're actually going to do a problem in a calculation that tells us about what the drift velocity is for electrons in a material. How quickly are they moving from right to left in this particular case? And like I said, it's slow, and our calculation is going to prove that and show that it's really depressingly slow. We had just finished describing how electrons move through the circuit and saying that we have to kind of ignore that for the most part and pretend that it's positive charge that's moving, even though we know the exact opposite thing is happening. And we finished with this idea of how fast electrons are moving and how they take this random sort of journey because of all these collisions, and they don't really get anywhere terribly fast. We are going to revisit this notion right at the end of the material for this chapter and do a calculation for the drift velocity. I don't know why these things are sort of out of sorts in this chapter. This is introduced early in the chapter, and I'm kind of sticking with that, and then it comes back to haunt us at the end. So I'm going to follow what it does in the textbook. So just keep in mind that this is what's happening. The bulk of the next little bit of this chapter, though, is dealing with something that probably a lot of you had in high school at some point, and that was Ohm's Law, because it's sort of a cornerstone of electrostatics, and it's really something that is really straightforward, and you can deal without having to approach it with a lot of mathematics. So it's often done in high school, and when a lot of this other stuff, such as electric field calculations, is ignored. It's more mathematically intense. So I think this will be pretty straightforward for most of you. So Ohm's law, we should start by writing that, and I have all of this space, so let's use up some of it. V is equal to IR. Don't forget, once again, that we're simplifying V there. That's actually a potential difference. So if you want to just imagine there's a delta in front of that. Potential difference is equal to the current times something new, which is the resistance. The resistance. And I should go ahead and tell you that the units of resistance is the ohm. And for ohms, we use a sigma to represent. Is that a sigma? Lowercase sigma? Omega? Oh, man, I'm just saying the wrong words. For whatever reason, I couldn't think of the right one. Omega. Is it a big omega or a little omega? Huh. Are there any Greek scholars in here? You're like, more than you, apparently. I get that. All right. So ohms, you will see that my omega gets a little messy at times, so I tried to draw it a little better there, but often it's going to end up kind of more like, or something kind of terrible, okay? So just keep in mind ohms is omega. So the first thing I need to point out about Ohm's law is this starting point, is that it's given this word law when it's really not a law, meaning it's not something that's obeyed in nature all the time. A better way to describe this might be Ohm's relationship, which no one's going to say that, I don't think. It just describes what happens sometimes with some materials. And it's a very useful thing when those materials, we could say, obey Ohm's law, but it's very often disobeyed. We're not going to do with the disobedience terribly much in this class. I just need you to know that it's not a hard and fast fact that always happens. So what it's trying to say is that essentially if I set up a potential difference across some material, proportional to that, current will flow. But inversely proportional to that, or rather if we think about it the other way, in opposition to that is the resistance. If I increase the resistance, we're going to get less current that flows for a given potential difference. So we have a linear relationship that is supposed to look like that in many materials. If I vary the potential difference, I'm going to get a current that responds directly proportionally to that. But keep in mind, it's possible to have something that looks like this, where we don't have this directly proportional relationship. So in the case of materials that do obey Ohm's law, we call that ohmic behavior. Big surprise. And if something looks like this, we might call that non-ohmic behavior. Okay, so the way we're going to treat most of this is that the battery, the power source, is trying to set up a constant potential difference, and the current is going to respond to that depending on how much resistance you have in the circuit. I saw a hand. You looked at the graph and you're good now? Okay, sounds good. Okay. Let me just point out once again here at the bottom, I don't know why this point keeps coming up, because maybe a lot of people have this as sort of a misconception. Just keep in mind that the same amount of current that enters the circuit at one point has to go through all the other parts of the circuit, and there's not like a creation of charge at any point. It's more like charge everywhere is moving, and we're not consuming charge. There's a conservation of charge that's happening as it flows in the form of current throughout the circuit. So, Ohm's law. We're going to come back to this in just a bit and answer a few questions. But just to help perhaps with labs that are upcoming, I don't think you guys have used resistors yet in a lab. What was the lab that you did last? It's like electrostatic voltage, electric field kind of stuff. Okay. So you're probably going to be doing DC circuits when we get back and playing with things like that. I just want to quickly point out that you will be using devices known as resistors, which simply exist to provide resistance in a circuit. They are still conductors. There's maybe the amount of conductance is varied a little bit so that I can regulate how much current flows in a part of a circuit. Resistors are just devices that look sort of like this, and they have a neat little color code to help us understand how much resistance is there instead of just printing the number on there, because often it's quite small. It's easy for me to see colored bands, but it would be difficult perhaps to read numbers that are on there. So you can see that there is a resistor color code made up of 4 different bands, and it simply works this way. Notice the one that we have here starts with a red. So you can see we use the number 2 for red. The second one is a green band. So for that, we have a 5. So the first 2 just give me the numerical values of the first 2 digits. The third one is a multiplier, and you can see for our multiplier we have a yellow band, so that goes here. That tells me the multiplier, so I'm going to multiply those digits just mashed together, not anything other than that, times 10 to the 4th. That tells me the resistance in ohms. But then the last one is either going to be gold or silver, and it's essentially telling me the tolerance, the uncertainty value, the plus or minus value on that. So you can see we have a silver band, which is plus or minus 10% of that value. Okay? Nothing terribly difficult about that. I just want you to be familiar with it. If you're sitting back thinking like, how do I know which direction to read the bands? Well, that last one is always going to be gold or silver. Start from the other side. Okay? Any questions or thoughts there? I think perhaps, maybe you can handle that. Perhaps, maybe. Anybody? Anything? By the way, I emailed earlier about our lovely microphone in here. It's working so far, right? It's been repaired. It's been taken care of. So if all fails today, then something is really terribly, terribly wrong. I don't need you going late like you were the other day, because that was not helpful, all right? Directly connected to Ohm's law, resistance is something known as resistivity. And this is something that, at least probably in high school, is often sort of sidestepped a little bit. Resistivity tends to be a slightly confusing concept, and it makes it a little difficult for me to explain. If it helps at all, and you understand already the difference between specific heat and heat capacity, the relationship between those two is exactly like the relationship between resistance and resistivity, okay? So it turns out, if I want to know the resistance of a given piece of material, I need a few different things. First of all, I need to know what material I'm using and sort of what its baseline opposition to current flow is, what its baseline resistance is. It's that thing that's known as resistivity, okay? So this, resistivity, is just a property of the material. It tells me something about the inherent resistance that's in that substance, okay? In addition to that, maybe I need to know how much of it I have. It kind of makes sense that if a little bit of a substance has a certain amount of resistance, well then twice as much of it should have twice as much resistance, and so forth, okay? So we have a couple of multipliers here that help us understand how much or what quantity or what distribution of material I have that's building up the total amount of resistance for that substance. In the numerator here, we have the length of the material. If I have to pass through more of the substance, it makes sense that it would offer more opposition or more resistance. But this is also divided by A, the cross-sectional area of the material. That one maybe is a little bit weird. So if you think about it, the area, if it gets wider, if it gets bigger, that material's offering less resistance, less opposition. Think of it like a highway. Same sort of idea. Like if I'm on a highway and only one lane is open, think of that as a small cross-sectional area. It's difficult to get all the cars through. If all of a sudden I double the number of lanes that are open, right? I've got 2 lanes to go through now. I've doubled the cross-sectional area. Traffic can more easily flow. There's less opposition. So more cross-sectional area offers less overall resistance, okay? So resistivity is about the material itself, and then we have the dimensions or the shape of that material and how much it adds up to give me an overall resistance. You get the concept? You get the idea? You're okay? Maybe I finally figured out how to say those words. Hello, are you out there? Anybody? I give up. I'm just going to sit down. I'll just take spring break right here in front of this trash can, which doesn't contain any bananas. That's good. Bravo. Yeah. By the way, my wife, for whatever reason, was cleaning out my car the other day because I tend to be a bit of a mess. In fact, we have determined I am physically an entropy bomb. Like, just if you're around me anywhere, like things are just in more disorder than they should be. So she's cleaning out my car because it was just a wreck. And deep within the car, the bottom of some bag that we had taken on a trip somewhere was an old banana. I knew something was wrong in my world. I just couldn't put my finger on what. Now I know. Life is looking up. She said that she was surprised she could get it from the car to the trash can without it completely disintegrating. She's like, it was just completely just ruined and gone. Yeah, there was a dark cloud in my life, but alas, that cloud has been lifted. I feel good and ready for spring break now. So, fantastic. I wonder why I didn't smell it. Shouldn't you smell an old banana? No? Do they not? I'm just not around bananas enough to know these things. It should. Maybe it was just covered up and sealed in a bag or something. I don't know what was going on. Anyway, I'm glad that's gone. I just feel good now. So, a few other different things that we should add to this. First of all, the resistivity of a material can vary quite a bit depending on a variety of different properties of that particular material. So, we might say that we have something like, I don't know, just like copper. There it is. We've got a piece of copper. You might immediately think like, I can just look up copper in a table and find out what its resistivity is. And if you look at that table specifically, it might tell you some additional things about how exactly that copper was made, exactly how pure the copper is. It might tell you that the value they're going to provide is at a certain pressure, a certain temperature. A lot of different external and internal factors impact the resistivity of a given material. So you have to be a little bit careful. So you can see I listed a bunch of et ceteras there. That should be enough to cover, there's a lot of different factors that can come into play when determining the resistivity of material. The one I want to focus on a little bit is the temperature dependence. The amount of opposition to current flow that a material puts up is based on the temperature because of what we said the other day. Remember the electron that's trying to run through the substance? And it's like this gauntlet of everything that's moving around. It's going to collide with stuff as it tries to pass through. As the temperature increases, there's more of that random motion. It's going to be harder for the electron to pass through without hitting stuff. Or you might think of it as it's going to have collisions more often, which impedes its progress. But if I make the material colder, a lot of that motion sort of start to slow down and freeze out a little bit, and maybe get reduced quite a lot if I go to lower and lower temperatures, which means it's going to be easier for the electron to pass through. So in general, at least for metals or for good conductors, the resistivity just increases with temperature. So if we were to graph that, it can't go all the way down to zero typically, but maybe it just looks kind of something like this. It just roughly increases with temperature, and it's probably not linear, but it may have a linear segment at higher temperatures. In general, it increases with T. If I step away from metals, if all of a sudden, maybe it's not a really good conductor and I start to move over into semiconductor land, things start to get a little ridiculous and a little complicated. And exactly what this graph looks like, the temperature dependence of the resistivity, can actually tell you a whole lot about, we could say, the electronic structure of the material itself on a microscopic level. You can learn a lot about how that material is put together based on how its resistivity varies with temperature. Let me add to this one equation, and I should pull my notes up, otherwise I'm going to write the wrong equation down. No, syllabus isn't right. Recent files. Chapter 25. Where's the one I'm looking for? There it is. Is that it? Yeah. So for this particular temperature dependence, we can write something like this. We could say that the resistivity, wait a minute here, at a given temperature is equal to some baseline resistivity times 1 plus alpha times T minus T naught, where this alpha is known as the temperature coefficient of resistivity. So if you happen to have any questions in the homework that pop up about what that temperature dependence looks like and how the resistivity varies as a function of temperature, at least for metals, you can start with this equation. We're not going to step away from metals really at all in this course, so you don't have to worry about the more complicated behaviors. Okay? A couple of other things I should add to this slide. One is the conductivity, which it kind of makes sense that would be the opposite of resistivity. Instead of how much opposition the material puts up, How well does it allow charge to pass? Okay? So it is exactly the opposite. In fact, it is the reciprocal of the resistivity. So the conductivity is the reciprocal of the resistivity. And I didn't mention that the units of resistivity are ohm times meters. So this is units of 1 over ohm meters. And then finally, back in the middle, I should give you a feel for what the numbers look like. So for conductors, values of resistivity are kind of in the range of 10 to the minus 8 ohm meters. If I'm dealing with insulators, you would expect that resistivity to be much, 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 much higher. Turns out that it is. It's more in the range of 10 to the 9 to 12th. So we flip all the way over to a positive exponent there, ohm meters. And of course, semiconductors are going to fall somewhere in between those two. And those can vary quite a bit, but I'll write those down as well. Let's say 10 to the minus 5th to like 10 to the 1. Resistivity, conductivity, temperature dependence, all of this stuff varies quite a bit. Okay? So, I'm going to go over to the next slide, and it is going to be ridiculous. It should earn a laugh, I think, that the question is so easy. And it's a little bit disjointed from what we were just talking about, but relates back to Ohm's law and circuits, etc. What is the correct way to light the light bulb with the battery? I'm bothered by this. Keep in mind that there is another, the other electrode for this is at the bottom of the battery. What do you think? Number one? I like number one. It's like you take a battery and a wire, and the wire just holds it. It's like, please light up. That seems like a nice way to light a battery, but that's not going to work. We don't have a complete conducting path there between the high and low potential, so that's not going to work. The second one, seems nice and everything, but all of this is just at the high potential. There's no potential difference that's being provided in the circuit, so that's no good. This is the only one that actually gives us a potential difference within the circuit and a complete conducting path. So hopefully you would understand that one that makes the most sense to light a light. What about this? You double a voltage across a certain conductor and observe the current increases by a factor of 3. What can you conclude? That is not a linear relationship, so Ohm's law in this particular case is not obeyed, although I do like answer number 3. This has nothing to do with anything. Next question. 2 wires, A and B, are made of the same metal, have equal length, but the resistance of the first one is 4 times that of the other one. How do their diameters compare? I'll give you a second to think through this one yourself. There's lots of extra space over here today. This entire row can be mine. When you have the answer, vote with your fingers. I'm glad that banana's gone from the board. That was bothering me all day the other day. Just so sad. Did any of you bring a banana today? No? Hey! Huh. And eat it later. Not now. Oh, the smell that would emanate from the banana if opened. Sad. Yeah. You know, plantains are interesting. Plantains, I understand they're very banana-like. However, if you deep fry them They are quite good. I don't know. No one's ever offered me a deep-fried banana. But I have had deep-fried plantains on menus elsewhere at various places. See, I think they know. They're like, we can't give you a deep-fried banana. That would be disgusting. But a deep-fried plantain, good. Can you eat a plantain like you do a banana? Just peel it and go? No? Okay, so there's some fundamental difference that makes one disgusting and one delicious if deep-fried, apparently. So what's the answer here? By the way, I appreciate those of you who just shook your head like, no, I don't have a banana. Like, I would never bring one to this class. You can forget that. Maybe others need to learn. The answer is number 4. Because it's the same metal, we have the same resistivity. Because it says they have equal length, that's the same. So if I want a factor of 4, and if we assume this is a circular cross-sectional area, since they gave us a diameter, half the diameter, and that's going to result in a square at the bottom, so it's going to give me 4 times the resistance. So half the diameter gives me 4 times the resistance. However, what if we change that just a little bit? A wire of resistance R is stretched uniformly, keeping its volume constant. You have a question? It's about bananas? I just walked by and you just can't. Do I look like a banana or something? What's up?
Have you ever tried the one? Like this very, essentially like a fried banana. It's like
No.
triangle, but instead of like stuff, it's a banana inside. And
How do you spell this?
T-U-R-O-N.
I haven't had this, no. I haven't heard of this, but, like I said before, I'm an adult. I can try things. I might. Why the laughter? You're like, no, you're not. You're not anywhere close to an adult. Okay, so let's write Tyrone. Is that how you say it? Or something kind of like that? Okay, I'll see what I can do. Good question. So let's go back to this equation once again. A wire of resistance R is stretched uniformly, keeping its volume constant until it's twice the original length. So you might imagine that its volume is essentially the cross-sectional area times the length. So if the volume stays constant, that means that when I double the length, we're putting a 2 here, and we're also cutting the cross-sectional area in half to keep the volume consistent. Well, that results in a factor of 4 for the resistance. I wonder why some of these are bold. It's almost like it's 4 or 5. Which one is the correct answer? Did you get 5? You're good? Everyone's happy? You're happy about that? Yeah, reasonably? I feel like I need to pull up a browser and look up this dessert you mentioned. Maybe someone else can. Okay? So that is all of those questions for right now. Does anybody have any questions, thoughts, complaints, anything at all? You've got the website up so we can look at this delectable treat? Can you click on one of those? I need to see it bigger. Where we go? It's interesting. I'm intrigued. I'll give you that much. Is it heavily in the banana flavor? Or does that get washed out by the deep frying? It's too bad. Just too bad. All right, so let's switch gears just a little bit and talk about energy and power, specifically electrical energy. And I'll let you read what's up there. I think it's kind of obvious that there are many types of energy. Electrical just happens to be a really convenient one that, I can carry around easily. I can power things in ways that would be terribly, we'll say, inelegant, that if we were having to use mechanical energy or something. I'm not even sure how you would use mechanical energy for, something like this. And I'm really glad that I don't have to directly convert mechanical energy into electrical energy like right with this. I appreciate batteries. Yes, that would be terrible. Like I have to do this the entire time, just trying to keep the screen lit up enough. And I'm like, if I slow down, all of a sudden it disconnects because the Wi-Fi drops. But I can still no, none of that's going to happen. So what I want to give you here is some equations for electrical energy and power. None of this is terribly difficult. So first of all, let's connect these two terms together. Energy itself can be related to power by this equation. Power times time is energy. So in other words, power is energy divided by time, so it's like a rate of energy consumption. Power is a rate that energy is being used or produced, depending on which way it's going. Also, power, has units of joules over seconds, or a new unit, which is the watt. Let me point out one little thing. If we were to go back to this equation and just take a look at the units, if power is in watts and time is in seconds, we've got a unit of power and a unit of time. Let's just switch that over to some other units that maybe you've seen before, and maybe let's make this one kilowatts. That's still a unit of power, and a different unit of time, maybe hours. Perhaps you've seen that somewhere before, the kilowatt hour, which is what you see on a power bill, which is a bit of a misnomer, right? It's just a straight-up energy bill. You're paying for energy, not for power, although you could convert between the two. But if you're charged for a number of kilowatt hours, you're directly paying for a unit of energy, okay? So let's see if we can come up with a few other equations here. So let me take this one. And I'm going to re-express it using some things we've done before. So instead of E for energy, let's write this as potential energy, and we'll write it in a differential form. So du dt. And I can re-express du in terms of electrical potential energy in terms of voltage and charge. So I could write that as dq times v over dt. And what is this thing? Charge over time. What was that? What was that? What? Louder? Current? Yes. Could be current. That is current. So we can rewrite power as current times potential difference. I think I'm going to start to do that every time someone answers a question. I'm just going to repeatedly say, what? What? And just get you to yell it over and over again. So power is current times potential difference. I can use Ohm's law now to re-express this two additional ways, which should kind of remind you of what we did with capacitors and how much energy they stored. We used Q equals CV to sort of re-express the equation a couple of other ways. So let's start by using Ohm's law to plug in for potential difference. If I do that, I'm going to get I times IR, which is I squared R. There's another way we can write power. Or, let's see, we could plug in for current, which is V over R. And then we're going to get, one more of these. I don't know what's happening with these arrows. Just deal with it. It'll be fine. V over R times V, which is V squared over R. So IV, I squared R, V squared over R, same thing, just expressed different ways based on plugging in Ohm's law. Okay? Was there anything else I wanted to say on that slide? I don't think so. Questions, complaints, comments? Nothing? You're just like, finish the chapter! Let us go. Yeah, you are. Everyone else wants to hear all of this. And they want to discuss bananas and plantains and what was that called again? Tyrone, perhaps. Yeah, we're going to have to look this up. So I want to briefly sort of go off the side here, simply because the textbook does, and I just want to point out a couple of things in case you're unaware of these. Using these power equations and talking about, the power that's being consumed around us all the time. If I write power as I squared R, and I think about current flowing through wires that have resistance, and even if it's a good conductor, it's going to have a low resistance unless I have a lot of wire. And you might imagine in a building or in a home, often that current is passing through quite a distance of wire, meaning the resistance isn't really negligible in wires and it can add up. And then if on top of that my current increases through those wires, the current is squared in that, and that can make the power kind of go high and off the charts. And typically this is comes in the form of heat. If you imagine that current is passing through wires that have resistance and there's a bunch of collisions, as more and more current goes through there and there's more and more resistance, there's more and more collisions, those collisions give off heat, and that heat could potentially become unsafe, especially if you decide to take your wires and wrap them in paper. I don't know who would do that, okay? But stuff could happen. Even with the insulator that we use on there, like a rubber or a plastic, if it gets hot enough, well, even that could start to break down and melt. And then maybe that becomes directly connected to wood or insulation in your home, and then life is terrible, right? No one wants any of that. So we have a couple of different devices that help with this. Fuses and circuit breakers will open the circuit, and remember, open means it's not going to allow current to flow anymore. In the case where the current gets too high, someone has done the work and determined that as long as we keep the current below this level, the power won't get too high and things won't get unsafe. If it goes over that level, things will be bad, so let's just never let the current go any higher. And these are some clever devices, specifically the fuse, I think, which you can see here. It's literally just something you put in the circuit that has a piece of metal that if it heats up a certain amount, it just melts. But it's self-contained in some glass, so it doesn't really do any harm. So if I zoom in on that a little bit, you can kind of see that metal filament that's going down the middle. It would melt, and then all of a sudden there's just a break in the circuit, and then physically nothing can flow anymore. It's kind of ingenious, kind of nice, but of course it's destructive. Once that melts, you got to get a new fuse. You can't just put it back together in some way, okay? Your question, or no? Okay. What was that? Oh, yeah, you get another. Good question. Apparently, since I answered it already. Yeah. What's up? I guess you could, but why? You know, it costs 50 cents or something for another one. You could try, but I'm not even sure what you're going to do with the glass in that point. Good luck. Please don't solder fuses back together. Just sounds like a bad idea. The other one is the circuit breaker. And notice hiding inside the circuit breaker is something we talked about back at the start of the semester. The bimetallic strip, where we have two different metals that expand a different amount when heated. And this time, that's what the current is passing through. And if it heats enough, you can imagine this thing would perhaps bend over here, and then it falls into that little notch. And when that happens, there's a little bit of a separation that occurs there, and that puts a break, a physical break in the circuit, and makes it open so that current can't flow anymore. This is the thing that exists, well, in that gray box that's somewhere in your apartment, right? When, you recognize the circuit breaker. When all of a sudden, I don't know, someone's making toast, and someone is cooking something in the microwave, someone else is blow drying their hair, someone has the stereo on, and it's not like, we're not using like an Amazon Echo. No, it's a stereo, like 1,000 amps of power. Like we have a stereo going, and all of a sudden you hear cha-ching, and the whole place goes dark. That's the circuit breaker that's kicking in. Someone wants to say something. No? We're going to let it go. What a stereo was. Wow. I have no comments on that. An audio playing device of your choosing. Yeah, I'm scared. I don't even want to ask why. Do you know what stereos are? Yeah? Okay, it's just you then. Let's see. So, here's what I want to warn you about. If one of two things is happening, if somewhere fuses are burning up and dying, or your circuit breaker in your house is repeatedly going off and you have to go back in there and be like, why did this happen? And then go back to doing all those activities again until and then and that's all this is happening all the time. Two things are possibly to blame. It could just simply be there is just too many devices, all of which are requesting current, and that's making I go up, so P is going up, and it's just like, this is too much for this house. I can't take it. Well, stop using as many devices. That's one option. The other thing could be that there's a fault somewhere, meaning something that typically uses a certain amount of current is now using way more current than it's designed for. This could happen if, say, there's what we call a short circuit occurring in a device, where instead of the current passing through whatever resistance is normally there, it's simply got a wire that's loose, and maybe it's touching the metal casing, and all of the current is just going through the metal casing where there's much lower resistance. So the current is spiking in the circuit because, well, that thing is not using the current that it's supposed to be. A fault could smell like something is burning a little bit. I have to ask, if you happen to use a hairdryer, does it smell a little like smoke? You know, it seems like after you have one for about a year, you're just like, I'm blow drying my hair. And it's like, smells a little burning in here. I wonder if that's my hair. No, it's probably inside. Something in there is burning just a little bit because there's a fault, because there's a short circuit, and maybe it's requesting a little bit too much current. And then, well, one hair dryer and one piece of toast makes the thing go, and you have to go back and it back again. Okay? So here's what I don't want you to do. Oh, also, if your hair dryer feels a little shocky, please get a new hair dryer or whatever device. If you push the little thing on the toaster down and you're like, it gives me a little spring in my step every morning. I feel a little buzz after touching the... No, replace the device. What you don't want to do is, I don't know, get too clever. I'm going to say something clever, and please don't ever do this. Don't be like, I need to run all of this stuff. So this little device that keeps flipping, I noticed it had a number 40 on it. I was at Home Depot, and I saw similar-looking devices that say 60. 60 is greater than 40. Maybe it would allow me to do more. I will buy that one and put it in its place. And then you're like, everything is working wonderfully. I can do all that I want. Well, you can for a while, but all you've done is bypass whatever safety calculations were done, and now you've decided to maybe go from a 40 amp maximum to a 60 amp maximum, 50% greater. Yeah. This sounds like a problem. Your stuff is working, but if you do this for too long, you're going to cause a fire and life is going to be sad. But at least you will go down with dry hair. Musically, because everything will be working fine. You will burn while eating toast. Ugh, it's all very sad. So please don't get clever, like either fix the fault if something feels a little shocky or smells a little burny, or just stop using so much stuff, okay? That's my safety warning for the day. Are you good? Yeah. What, your blender is manual? Oh, you read the blender manual. Got you. I thought I was like, that could happen, yeah. So if your device is new and it smells a little burny at the start, that's probably okay. If you've had it for a while and maybe dropped it 18 times, then the burning smell is probably not residue at that point. It's probably your fault for dropping things and now it's broken. So don't use as much stuff or replace the device. Yeah. No, I'm actually not. It feels realistic, though, doesn't it? Yeah. I've been around people. I've lived with people. Circuit breakers have gone off. I don't know, maybe I'm hiding things. I'll just continue. Why not? There's 2 more things in this chapter. Question first. Yeah. I said, don't be, quote, clever. Okay. Where are you putting this paper clip? Yeah. Mm-hmm. Well, the actual turning off is a split second. So it's like once you hit some value that could potentially be dangerous going forward. We're not talking about maybe being shocked. Yeah, but also this isn't the best device to protect against shock. It's protecting against fire. There is something else that can help you with shock, which I can't remember when we talk about that. Magnetic fields. We need magnetic field stuff to get there. And that is that little box on the end of the hairdryer. The plug that's got, it's never just a plug, right? It's a little box plug. There's a device in there that's helping you as well. So don't ever take that off and say, ooh, 2 wires. I'll just plug those in. Hairdryer forever. Don't do that. That device is there to help you. But we will address that when the time comes as well. That one can happen fast, and it'll protect you against shock. Shall we continue? Last 2 things. This one is just a setup for a later chapter, okay? It's very disjointed from what we're just talking about now. I don't know why it's in this chapter, but I'm going to give this information to you anyway. Alternating current, everything that we've talked about so far, as well as everything we're going to talk about in the next chapter, is known as direct current, meaning the current goes in one direction with one value the entire time. Alternating current is what happens in the real world a little bit more often. Okay, so if I plug something into the wall over here, alternating current is what's being provided there. So instead of something that looks like this, where constant current, it's direct, we have something that looks like what's right below it. Yes? There are opinions and arguments on that. We picked one a long time ago. If I understand correctly, there was a fight over it like 100 years ago, like Tesla and Edison. By the way, boo Edison, yay Tesla in general. Tesla died what? At like 30. See, that's sad. How much more could he have done? Anyway, let's hope that he didn't use a hairdryer in the wrong place, the wrong time. I don't know. So my understanding is that alternating current or direct current could have been used, but alternating current does help us over long distances. The losses aren't as great when we try to transmit it from, say, a power plant somewhere else. Why? It's more about being able to, we'll deal with this in a couple of chapters, but we can ramp up to a higher voltage in a way that allows there to be less current that's flowing so that there's less power loss along the route. But I will agree that it seems like, well, we have something so simple. Why deal with something that looks so complicated? Okay? There's a lot of interesting things that happens with alternating current. I'm going to give you just a couple of basics here. The first thing I want to point out is that you'll notice we go from positive to negative, meaning that the direction of the current changes, and it's changing rapidly. But it's not just going like full tilt one direction and then full tilt the opposite direction and so forth. It's not a step function. Instead, it's alternating and varying in magnitude as well. So it goes higher and higher and higher one direction until it reaches a peak, and then scales back until zero, and then starts to build in the other direction and grows and goes back to zero. So it's not just directly increasing and decreasing. What else to add to this? Why is this device not working? Scroll down. There we go. So we could represent both this or the voltage with a sine function. So we could write something that looks like this. We could say that the current as a function of time is the peak current, the largest it ever gets, times the sine of omega times time. Omega is equal to 2 pi times the frequency and is known as the angular frequency. So the frequency is just the number of times that it oscillates each second. So higher frequencies are more rapidly oscillating between the two peaks, positive and negative. So the current is always changing, but also we could write something similar for the potential difference that's being applied, and it looks exactly the same, like so. I should point out that alternating current used in this country, so let's say in the U.S., the frequency is 60 hertz. Elsewhere in the world, it's 50 hertz. Why can't we all just get along? I wonder if all of the world's problems would be solved if we could just agree on a frequency. It seems like that'd be at least a start. Like if we can't agree on something like this, how are we ever going to agree on anything, it seems? But so a lot of the world uses 50 hertz. We use 60. This is the reason why you need international adapters. It's beyond just like the plug is shaped differently if you travel internationally, right? The holes are in different places. Also, you have to be careful because your device might want 60 hertz and you're being provided 50. Yes?
Why are we so different?
Boy, that is a big question. Why are we so different? What's that? Why aren't we all the same? Are we all the same, but different? I can't even begin to answer that. People just picked a number. Yeah. Yes. When was the end of his life? 86. Well, that's quite a bit different than 30. Oh, fell in love with a pigeon. Well, I don't think that's crazy. Pigeons are nice. I don't know. Go ahead, question.
When you talk about the current switching directions, on that circuit diagram that we had a couple slides ago, showing like the current going the other way and the opposite of the electron.
Yeah.
So if you were to think of it as like electrons like that, does that mean like the electrons are going one direction, like they're physically like
Yes.
instead of all in just that one big loop?
Yes. So it's like we take all the electrons in the circuit and tell them all, like, let's all go counterclockwise. And it's like, and they all go that way, like faster and faster, you might think of it. And then reach a maximum and then start to go all the other way and over and over and over again. Sounds exhausting for an electron. So don't be one. I don't know why you would be. The only other thing that I want to put on this slide is going to come up later. You will notice that, well, if the current's always changing, and maybe I don't really care to find what the current is at a particular moment in time, but I just kind of want to get a feel for, like, how much current are we using? What is the, say, average value of the current that's being applied to a circuit? Well, an average here is going to be a little bit useless, don't you think? What would the average current be for that graph? Over, a period of time, 0. We got equal positives and negatives. So it would be like for every circuit always that has alternating current, average current, 0. So that's no good. So instead, we use some other values that are appropriate, and often we use what's known as the RMS voltage and the RMS current. And this is just equal to the peak current divided by the square root of 2, and the peak, whoa, I did those backwards. That is just terrible. I was thinking the other way around. The peak voltage divided by the square root of 2, and the peak current divided by the square root of 2. If you look at a device that's going to use alternating current, you might see two numbers that are printed on there. If it just gives you a value for the potential that this device needs or the current that it needs, and it doesn't specify, it's probably the RMS. If it does specify peak, then, well, you know what that is. It could give you both values as well, which is another option. So peak is of interest, RMS is of interest, but average really doesn't do us any good, which brings us to the last couple of slides and takes us back to the idea of the electrons moving with a drift velocity. By the way, all that alternating current stuff, we'll come back to that. Chapter 30, I think, is about alternating current circuits, so we'll revisit that. This is more of just an introduction to let you know that there's stuff besides the direct current that we're dealing with. So let's take a look at the microscopic view of current, thinking about the electrons that are moving instead of just imagining like this bulk of electrons that are flowing from one place to another through a circuit. I can give you a couple of different quantities here that will be of use. First of all, it's written right there, but I'm going to write it again. The current density is equal to the current divided by the cross-sectional area. You could think of I, the current, as sort of being the bulk value. It's like how much total is passing through the wire or through the conductor at a point. J is more like going to different points within the conductor and asking sort of how dense the flow is at that particular point in the conductor. The current density is the total current divided by the cross-sectional area. We can also relate this to the electric field by another quantity we learned about today. So we could say that the J vector is equal to the conductivity times the electric field. So an electric field is set up in the conductor because there's a potential difference. It tells all the electrons to go from one side to the other. And this finally connects something that we've been talking about over and over for several chapters now, the electric field, to something physical that's happening in the circuit that we know as current, but we have to express it as current density to sort of get the overall effect. One other thing that we can do here is describe how fast these electrons are moving. hear a squeaky door. Did someone stick their head in? I kind of want to, like when I hear someone at the door, like to run over there and just be like, hello! And just freak out whoever it was that just peered into the room. But that'd just be mean, wouldn't it? I really shouldn't do things like that. It'd just be terrible. So let's put a couple of things together here. First of all, let's start with our bulk property, the current, and see if we can get all the way down to figuring out how fast the individual electrons are moving. So we know current is an amount of charge that's moving in a particular amount of time. An amount of charge moving in a particular amount of time. And then I'm going to make a bit of a leap. An amount of charge we can sort of expand out and express this way. So first of all, we know that each individual charge has the elementary charge. So that's minus E. That's a start. But how many of these charges do I have? Well, we could do something like this. We could say, and let me not use a symbol here, times the number of charges per volume. And then we're going to multiply that by the volume that's containing those charges. Work that back through and make sure that makes sense to give you a total amount of charge Q. So a number of charges per volume, so charge per volume times volume, that's just a number of charges. And then I'm going to multiply that by how much charge each one has. That should give me a total amount of charge that's there. Yes? Huh. Well, let's zoom in and find out. Got to say, it looks a lot like a Z, but it's not supposed to be. That's now a plus sign, kind of a comma, a dash, and a hyphen. So let's do that again. Yeah, that's just an equal sign. There we go. Sorry, that was a longer answer than was required for that. But so let's take this a step further, and we're going to plug in something for the volume using this diagram down below. So the volume is just maybe a space within our wire that we describe by this. And we could say that the volume is equal to the cross-sectional area times the length of the wire that we're particularly talking about at this point. And that would be the same as the cross-sectional area times, let's describe the length as how far an electron has traveled during a particular amount of time. So I could say that the length is an amount of time times the velocity of those electrons. So velocity times times gives me a distance. Okay? Yeah. You could think of it that way. Yeah. A fixed, arbitrary volume. Okay? So let's take that and plug that in for volume. And I'm going to use a lowercase n to represent the number of charges per volume. So that means now we have minus E times n times this volume thing, which is A times delta T times the velocity, the drift velocity. And please, let's not leave out that delta T in the previous step. All of that was over delta T. So the delta T's cancel, and now I have current is equal to minus E N A times the drift velocity. Notice what we have here. We've got a connection between a macroscopic quantity, right? You might remember we did something like this back in thermodynamics as well, connecting these two worlds. Macroscopic, I can take my instruments and say how much current is passing through that wire. I can easily make this reading. Microscopic is how fast any individual electron is actually traveling. How would I ever measure that? I don't have a microscope that good, right? I can't be like, look at that electron go. How fast is he moving? Like, I can't measure that directly. But we can take the macroscopic quantity and do this calculation to find out how the microscopic objects are moving. That's kind of interesting and kind of useful, okay? So we could do one more thing here and divide this whole thing by A. So let's divide that side by A and divide the other side by A, which gives me minus E in drift velocity. And that is what we called earlier the current density. So we can express that either way. Drift velocity connected to the current or the current density. So to wrap things up, I want to use that particular equation and see if we can get a number for how fast these electrons are moving. Yeah, I really want to. I'm just not brave enough. Maybe next time one of you, like if someone sneaks in just a little bit, one of you just sprint to the door. Don't push it open too fast, though. You might hurt someone. That would be kind of sad. Maybe just run to the door and yell. That'd be kind of nice to hear a yell from the other side. Ah! Ah! They're probably listening, waiting for the next thing. It's probably my boss or something. That'd be kind of sad. So how fast do the electrons move? Let's use that equation with just some given values. Let's consider a copper wire, which is used pretty frequently in a lot of different circuits. It's a common conductor that's used for a wire. Let's say that it has a cross-sectional area of 0.5 millimeters squared. So small little wire. So let's see, that's going to be 0.5 times 10 to the minus 6 meters squared. And we're going to let a current of 5 amps pass through that. A number that we can look up is the charge density that's in copper. And it is about 8.5 times 10 to the 28 charges per meter cubed. There's a lot of electrons in a meter cubed of volume of copper. Lots and lots and lots of free electrons. And we can plug these numbers into our equation. And we're just going to find the magnitude of this, so I'm going to leave out the negative sign. So En, drift velocity, times the cross-sectional area, and we'll solve for the drift velocity. Yeah, sorry. Experimentally. Someone had to do experiments on this to find the number of charges. There's something known as the Hall effect. You can do a Hall measurement that allows you to measure the number of free charges. So that's about all I can tell you at this point. It's a number that we can actually measure. You can do theoretical calculations as well, but that's a whole other issue. So let's plug those numbers in, and I'll tell you what you get. I've got 0.000735 meters per second. That's depressing. Or a quick conversion tells me that's about 3/4 of a millimeter every second. Aren't you glad we don't have to wait on the charges to go from one point to the other? Aren't we glad they all move at once? So every second, about that far. That is just depressingly slow. All of that bouncing around takes its toll. It takes a long time for one charge to go all the way around a circuit. Yeah. I'll let you convert that. I don't know. That felt like a test. Can you do it in this unit? Can you do it in this unit? Yeah. Yes. So what we mean by this, if we look at our cylindrical conductor again, so maybe the electron is at this location, and we want to see how long it takes for it to get somewhere farther down. In between, it might do all of these sorts of things before it travels that particular distance, L. But we're just using that raw distance between those 2 points to calculate that velocity. Yeah, exactly. In the back. I'm sure it does, yeah. But the overall net result is forward motion because the electric field is forcing it that way. Yeah. It's a good point. We're looking at a couple of different things there. A technical question, perhaps. Before, we were looking at individual charges and how that affected an electric field that's in a conductor. Here we're talking about sort of an external potential difference that's been set up at two ends of a conductor. If it helps, maybe you could think of the electric field that's set up sort of occurring along the edges, but that's not really true either. I don't have a good way to explain the bridge between those two ideas. Yeah. Where? What? How? This? 5A. 5. 5 amps. Yes. There would be a different mean free path here. I'm sure there must be some relationship between the two. There we were just looking at just random motion of the particles moving about in between collisions. Here we're giving them a push. So if anything, I would expect this value to be a lower value from before because we're kind of forcing them in one direction. There should be some relationship between, say, the thermal mean free path and the electrical mean free path, though. But I'm not sure what that relationship is. Good question.